Skew and kurtosis. Skew is caused by the value of the outlier terms. In other words, this determines the tail length. Kurtosis, on the other hand, is caused by the frequency of these outlier terms, and therefore it affects the tail width. So let's just stop there just for a second. So when you think of skew or kurtosis, you're thinking about the outlier values. So these are the extreme values at either end of the distribution. So the really, really high numbers or the really, really low numbers. Now, what do you want to know about these extreme values? Well, first of all, what are their values? So for example, if I'm looking at a positive outlier, is it plus 100 or is it plus 100 million? So tell me the value. And the other thing is, tell me about the frequency of these values. So let's just say the outlier value is 55,000. Well, how often does that observation occur? Like, how often do you see 55,000 in the data set? And as we're going to see when we look at our visual illustrations, when you're looking at outliers, because you're looking at the extreme values on either side, it affects the tail of the distribution. Because you can see, just jumping ahead a little bit, the tails represent either the really, really large positive numbers or the really, really large negative numbers. So that's where all these components in our definition are coming from. So first, let's dive into skew. A reminder again, skew concentrates on the value of these extreme numbers. So in the first case, we have zero skew. And what that means is that the outlier values are the same on both sides of the distribution. So the large positive numbers and the large negative numbers are equal in magnitude. So therefore, it results in a symmetric distribution. So both tails, the positive tail and the negative tail, have the same stretch, if you will. So if these two are stretching at the same rate because the positive and negative numbers are equal in size, then the distribution will remain symmetric. So then the analysis becomes as follows. If the distribution is indeed symmetric, in other words, you could see that if I sort of cut a line there, this side looks like the mirror opposite of that side, and that's what symmetric means. What conclusion can you draw about these measures of central tendency? So if it's symmetric, the arithmetic mean will be equal to the median, which will equal to the mode. Right? And from a previous module, we've seen what each measure of central tendency represents. So the average, just very quickly, the average looks at the average of all the values. On the other hand, the median just looks at the value of the middle observation, and the mode is the observation that occurs the most number of times. And you can see why this would be the mode, because if you're looking at the scale, that scale measures frequency or probability. In other words, this tells us, the scale tells us how often does each value occur, right? And you can see that this value, which in our symmetric illustration is the average or the median, this occurs the highest number of times, so it's the most frequent. But that's the definition of mode. It's the observation that occurs the most number of times. So this really is our base case, I should say, when you have sort of a zero skew. But now look what happens when we change the skew. So in the case 2, we have positive skew. And what positive skew means is that the positive outlier values are larger than the negative outlier values. So here's the distribution. So here's the positive values, and more specifically, these are values that are above the mean, whereas these are values below the mean. But nevertheless, you could see the magnitude here versus the magnitude there. So this is what positive skew means. It says these positive outlier values are much larger in size than the negative outlier values. So if that's the case, you could see that the stretch on the right side is greater or lengthier than the stretch on the left side. And as a result, you could see that the distribution gets pulled to the right side. And then you get the following visual, or the following distribution. Okay? And you can see how the distribution is biased towards the positive side, because the positive numbers are so large. Okay, now, ladies and gentlemen, when we get to the distribution, the next task is to determine how the measures of central tendency are lined up. Now, the easiest measure of central tendency to spot is the mode. Why? Because remember what mode is. Mode is the observation that's observed the most number of times, i.e. the most frequent. Well, the most frequent is right there. So this here represents our mode. So the hump. So the hump corresponds with the most frequent observed value, and that's our mode. So my suggestion is you start off with the mode. Now, the only thing you have left is median and arithmetic average. But what distinguishes these measures of central tendency from each other? The mean, or the arithmetic mean, looks at all values, including the outliers. So since the outlier values have such large positive values, the mean is going to be pulled in the direction of the skew. In other words, it's going to be going towards the positive side. So between the median and the mean, it's the mean that's getting dragged further to the right. Because the median doesn't care about these outlier values. The median just concentrates on the middle observation. But the average, on the other hand, looks at the all values. So if you got some really large positive values, like I said, the arithmetic mean is going to get pulled further to the right. So once you've done that, ladies and gentlemen, you can draw your conclusion. So if a distribution is positively skewed, the mean will be greater than the median, and the median in turn will be greater than the mode. Or you can just jump the gun. So on the exam, they're just comparing mean with mode. For positive skew, you could tell that the mean will be greater than the mode. Now here's where you got to be a little bit careful. A lot of candidates might see the label as positive skew and assume that most observations are positive. Actually, it's the opposite. If the distribution is positively skewed, you can see that the mean is here, and therefore most of the observations will have values that are below the mean. And there it is. In a positive skew, most observations will lie below the mean. So why is the mean so high? Because you have a few positive outlier observations that have very, very large values. And I'll give you a good analogy. So suppose that Bill Gates moves in your neighborhood. What would happen to the average income in your neighborhood? So if Bill Gates is living in your neighborhood, the average income would go through the roof. But then if I asked you, would most households have income below or above the average? Well, most households would have income way below the average. The only reason the average is so high is because you have this one individual who's pulling up that average to astronomical levels. So now let's use the exact same analysis for negative skew, and negative skew implies that the negative outlier values are larger than the positive outlier values. And again, we're going to do the same analysis as we did with positive skew. So since the negative numbers are larger, the stretch on the left side is greater than the stretch on the right side, because these negative numbers are much larger. So if that's the case, you get the following distribution right there. And then after that, you have to line up your measures of central tendency. Once again, the easiest measure of central tendency to identify is the hump, because the hump represents the most frequently observed value, and that's the mode. So then the next question is, how do we position the mean and the median? Well, between the mean and the median, which of these measures actually looks at the value of these outliers, the average or the mean? So therefore, it's the mean that's going to get dragged towards these large outlier values. So then, once we've positioned all these measures of central tendency, you can draw your conclusion that in a negative skew, the mean will be less than the median, which in turn will be less than the mode. Now note, in a negative skew, again, you have to be a little careful here. So in a negative skew, do most observations lie above the average or below the average? So don't be fooled by the negative, right? You have to look at the actual distribution. So in a negative skew, it looks like most of the observations lie above the mean. Okay, so there it is. So now we're going to look at the next description for tail, and that would be kurtosis, and its related excessus kurtosis. And excess kurtosis is just kurtosis minus 3. And we have 3 scenarios here. In case 1, we have normal distribution. And remember what kurtosis does. It looks at the frequency of the outlier values. So in a normal distribution, so the frequency of the outliers would be normal, quote unquote. And so this is our benchmark. This is our base case. And if the distribution is normal, meaning that the frequency of the outliers is just normal, kurtosis would be 3. And since excess kurtosis is just kurtosis minus 3, 3 minus 3 is equal to 0. So that's our base case. And again, I remind you, kurtosis refers to frequency, which really translates into tail width. So in the second scenario, we're looking at leptokurtic, and here the outliers occur more frequently than normal, therefore resulting in wider tails. What's the connection? Remember the vertical scale measures frequency. In other words, how often do we observe these values? So here's the outlier. So we know the outlier is occurring in the tails, right? But normal says, so assuming this is our benchmark, the normal, so the red line is normal. So if you tell me that the outliers are occurring more often, so here's an outlier right there, and normal says it occurs this many times. But actually, if it's leptokurtic, it means it's occurring that many times. So it's occurring more often than normal. So that's why you get wider tails. You could see, so this is the tail area, and with leptokurtic, you could see that the tail is wider versus just the normal. Now, if it is leptokurtic, here's how the metrics are going to measure out. Kurtosis would be greater than 3, and as a result, excess kurtosis will be greater than 0. So if kurtosis was actually 4, excess kurtosis would be 4 minus 3, be equal to 1. And the other scenario for kurtosis, would just be the opposite of lepto. And this is called platykurtic. And where leptokurtic had more frequent outliers, naturally platykurtic would indicate that the outliers occur less frequently than normal. So again, the red line represents normal. So according to normal distribution, these outlier values occur this many times. But if the outliers exhibit a platykurtic distribution, that same outlier values would occur less frequently. And you could see why it's called narrower tails, right? Because under normal, here's the tail width, but under platykurtic, the tail is a lot narrower. And if it is indeed platykurtic, the kurtosis would be less than 3, and therefore excess kurtosis would be 0. So with platykurtic, let's just say the kurtosis is equal to 1. Excess kurtosis would be 1 minus 3, and therefore it'd be negative 2. So now that you've seen skew and kurtosis, what would be the absolute worst case scenario for portfolio or stock return? Well, in the first case, it would have negative skew. That's pretty bad because it means that these negative outlier returns are much larger. So where you thought maybe minus 20% was a worst case scenario, Now minus 50% is more likely. So you see that the negative values are getting larger, and that's what negative skew is. And at the same time, excess kurtosis is greater than 0, meaning that these very large negative outlier values are occurring more frequently. So where before maybe you thought you might lose minus 20% every 20 years, now with this scenario, we're saying maybe you lose minus 50% every 4 years. So you're getting much larger returns and occurring more frequently, and therefore that would be a worst case scenario.